Welcome. Today we're diving into the world of CO2 sequestration, a promising approach to managing carbon emissions and combating climate change. While improving energy efficiency and increasing non-fossil energy use are vital, carbon sequestration offers a complementary path. This strategy allows us to continue benefiting from fossil fuels while protecting our climate. Many people think of planting trees when they hear carbon sequestration, but the focus here is on capturing CO2 from large stationary sources like power plants and storing it safely underground or in the deep ocean. Let's explore the opportunities and challenges ahead. Fossil fuels currently supply over 85% of the world's energy needs, powering our industries and homes. They have played a major role in raising living standards globally. Over time, we've improved how we extract energy from fossil fuels, reducing pollutants like NOx and SO2. However, despite these advances, the future of fossil energy is uncertain due to concerns about climate change, often called the greenhouse effect. The main culprit is carbon dioxide, or CO2, released from burning fossil fuels. If we can capture and store this CO2 efficiently and safely, we can continue to use fossil fuels while addressing environmental concerns. Interestingly, the idea of capturing CO2 from power plant emissions didn't begin with climate change in mind. Initially, it was seen as a way to provide CO2 for enhanced oil recovery, where CO2 is injected into oil reservoirs to boost production. Several commercial CO2 capture plants were built in the US during the late 1970s and early 1980s. However, when oil prices dropped, these plants became too expensive to operate for oil recovery, and most were closed. Later, new plants emerged, driven by economic incentives and the need for commercial CO2. This history set the stage for today's focus on climate-driven CO2 capture. Beyond power plants, many industrial processes emit large amounts of CO2. For example, natural gas operations often produce CO2 as a byproduct, which must be removed to meet pipeline standards. This makes natural gas facilities logical candidates for early CO2 capture and sequestration efforts. Looking ahead, producing hydrogen-rich fuels from carbon-rich sources like coal or biomass could also generate relatively pure CO2 streams, making capture more feasible. These developments open new avenues for integrating CO2 capture into various sectors, not just electricity generation. Major milestone was reached in 1996, when Statoil of Norway began storing CO2 from the Sleipner West gas field in a sandstone aquifer beneath the North Sea. This project injects about 20,000 tons of CO2 per week, equivalent to emissions from a mid-sized coal power plant. The economic driver was Norway's carbon tax, which made sequestration financially attractive. The operation costs about $15 per ton of CO2 avoided. This pioneering effort is closely monitored by international researchers, providing valuable insights for future projects worldwide. Currently, most commercial CO2 capture from power plants uses chemical absorption with a solvent called monoethanolamine, or MEA. Developed over 60 years ago, MEA is effective at removing acid gases like CO2 from gas streams. However, capturing CO2 from flue gas requires large equipment and significant energy, which reduces the net power output of the plant. For example, a 500 MW coal plant may lose 20% of its output after installing CO2 capture. This energy penalty is a key factor in the overall cost and feasibility of CO2 capture. The energy penalty for CO2 capture varies by power plant type and technology. Today, conventional coal plants face penalties of 27–37%, while advanced coal plants and natural gas plants have lower penalties. However, future improvements could reduce these penalties significantly. For instance, advanced coal plants might see penalties drop to 9%, and natural gas plants to around 10%. Reducing the energy penalty is crucial for making CO2 capture more economically viable and less disruptive to power generation. Researchers have analyzed three main types of power plants for CO2 capture. Advanced coal plants using integrated gasification combined cycle IGCC, conventional coal plants using pulverized coal PC, and natural gas plants using natural gas combined cycle NGCC. Each type uses different processes for generating electricity and capturing CO2. IGCC plants gasify coal and remove CO2 from the resulting gas, while PC and NGCC plants use MEA scrubbing to capture CO2 from flue gases. These differences affect both the cost and efficiency of CO2 capture. Compare the economics of CO2 capture. Studies look at both reference plants without capture and capture plants with CO2 capture. Key data points include the cost of electricity, capital costs, net power output, CO2 emissions, and thermal efficiency. Researchers adjust these studies to a common economic basis, considering factors like fuel costs, capital charge rates, and annual operating hours. This approach allows for fair comparisons across different plant types and technologies, helping identify the most cost-effective options for CO2 mitigation. Two main metrics are used to evaluate CO2 capture: mitigation cost and incremental cost of electricity. Mitigation cost, measured in dollars per ton of CO2 avoided, helps compare different strategies such as sequestration versus energy efficiency. Incremental cost, measured in cents per kilowatt-hour, shows how much electricity prices would rise with CO2 capture. Both metrics have strengths and weaknesses, and understanding them is essential for policymakers and developers considering carbon management options. Analysis shows that reference natural gas plants have the lowest electricity costs, around 3–4 cents per kilowatt-hour, while coal plants are slightly higher at 4–5 cents. When CO2 capture is added, costs rise. NGCC capture plants reach 5-6 cents, IGCC capture plants 6-7 cents, and PC capture plants 7-8 cents per kilowatt hour. This means that with current technology, coal is at a disadvantage compared to natural gas, but advanced coal plants could become more competitive if CO2 regulations are enforced. Looking closer at the incremental cost of electricity due to CO2 capture, IGCC plants show the lowest increase, ranging from 1.1 to 1.7 cents per kilowatt hour. NGCC plants see a rise of 1.9 to 2.1 cents, while PC plants experience the highest increase from 2.3 to 3.1 cents. This suggests that, if CO2 emissions are regulated, IGCC plants could be the most efficient option for meeting climate goals through sequestration, provided they become more competitive with NGCC reference plants. Mitigation cost is a crucial metric for comparing different CO2 reduction strategies. It's calculated by looking at the cost difference between a reference plant and a capture plant, divided by the amount of CO2 avoided. The choice of reference plant affects the result. Using IGCC as the base gives a mitigation cost of $26 per ton, PC gives $29, and NGCC gives $107 per ton. This variability highlights the importance of context when evaluating carbon management options. Mitigation costs discussed so far only cover the capture process. To get the total cost, we must add the expense of transporting and injecting CO2 into storage sites, such as underground reservoirs or the ocean. Preliminary estimates suggest this adds another $5 per ton of CO2 avoided. These additional costs must be considered when comparing sequestration to other climate mitigation strategies. Current CO2 capture technology is relatively expensive, but there's significant potential for cost reduction. Improving the thermal efficiency of power plants, developing better separation technologies, and reducing the energy penalty can all help lower costs. In the future, entirely new types of power plants and innovative power cycles could further drive down expenses, making CO2 capture and sequestration more attractive and widespread. Better understand the economics of CO2 capture, researchers plan to develop models that test how different variables affect costs. These variables include plant heat rates, energy penalties, capital costs, and fuel prices. By running sensitivity analyses, they can identify which factors have the biggest impact and where improvements will be most effective. This modeling work is essential for guiding future research and investment in carbon management. Once CO2 is captured, the next challenge is what to do with it. While some commercial uses exist, such as in chemical processes, they only account for a small fraction of the billions of tons produced annually. The real opportunity lies in storing CO2 underground in geological formations or in the deep ocean, both of which have the capacity to handle large volumes. Let's look at these options in more detail. Geological formations suitable for CO2 storage include deep saline aquifers, depleted oil and gas reservoirs, and unmineral coal seams. These formations are widespread and together could store hundreds to thousands of gigatons of carbon. The technology for injecting CO2 underground is well established, especially in the oil industry. For example, enhanced oil recovery projects already inject millions of tons of CO2 each year. Geological storage is currently being demonstrated in projects like Norway's North Sea aquifer injection. Estimates suggest that the ocean could store thousands of gigatons of carbon, while deep saline formations in oil and gas reservoirs offer hundreds to thousands of gigatons of capacity. Unmineral coal seams in the terrestrial biosphere provide smaller, but still significant storage potential. In contrast, commercial utilization of CO2 is limited to about 0.1 gigatons per year. This highlights the importance of geological and ocean storage for large-scale carbon management. Oil and gas reservoirs are attractive for CO2 storage because they have already contained fluids under pressure for millions of years. In the US alone, abandoned reservoirs could hold about 3 billion tons of CO2, while ultimate reserves could store up to 100 billion tons. Injecting CO2 into active oil fields can also enhance oil recovery, helping offset some of the costs of sequestration. This dual benefit makes oil and gas reservoirs a promising option for early projects. Deep saline formations, located more than 800 meters underground and separated from surface water supplies, may offer the best long-term storage option. Their potential capacity is vast and they are widely distributed. However, less is known about their properties compared to oil and gas fields, leading to some technical uncertainties. Ideal formations have an impermeable cap to trap CO2 and high permeability below to allow efficient distribution. Ongoing research aims to address these uncertainties and ensure safe, effective storage. CO2 is stored underground through several mechanisms: displacement of existing fluids, dissolution into those fluids, and chemical reactions with minerals to form stable solids like carbonates. Initially, displacement is the main process, but over decades and centuries, dissolution and mineralization become more important. These mechanisms help ensure that CO2 remains securely stored over the long term, reducing the risk of leakage back to the atmosphere. Abandoned or uneconomic coal seams offer another storage option. CO2 can diffuse into the coal's pore structure where it is physically adsorbed, much like activated carbon filters impurities. This process can also enhance the recovery of coal bed methane, providing an additional economic incentive. While still in development, pilot projects have shown promise, and further research is underway to scale up this approach. Despite its promise, geological storage faces several challenges. Key issues include uncertainties about available storage volumes, long-term integrity, and the costs of transporting and injecting CO2. Ensuring storage integrity is vital to prevent unintended releases, protect public safety, and avoid liability. Fortunately, the oil and gas industry has extensive experience managing underground fluids, which can be leveraged to address these concerns. Ocean is the largest potential sink for anthropogenic CO2, already containing about 40,000 gigatons of carbon. In comparison, the atmosphere holds just 750 gigatons. Each year, the ocean naturally absorbs about 2 gigatons of carbon from the atmosphere. Directly injecting CO2 into the ocean could accelerate this process, helping to reduce peak atmospheric concentrations and slow climate change. However, this approach comes with its own set of challenges and uncertainties. The ocean is structured in layers, a mixed upper layer, a thermocline, and a deep region. CO2 behaves differently depending on depth, temperature, and pressure. Above 500 meters, CO2 is a gas. Below that, it becomes a liquid. At certain depths, CO2 can even form solid hydrates. Understanding these behaviors is crucial for designing effective and safe ocean sequestration strategies. The near term, the most practical strategy is to inject CO2 below the thermocline, at depths of 1,000 to 1,500 meters. This can be done using pipelines from shore or by transporting liquid CO2 by tanker and releasing it through a pipe towed by ship. Both methods create rising plumes of CO2, and research is ongoing to optimize injection techniques and minimize environmental impacts. Another approach is to inject CO2 as deeply as possible, potentially into seafloor depressions at depths of around 4,000 meters. Here, CO2 could form a deep hydrate lake, maximizing sequestration efficiency. However, this would require new technology and comes with unknown costs and technical challenges. Research continues to explore the feasibility and safety of such deep ocean storage. Implementing ocean sequestration requires research on several fronts. First, sequestration efficiency. How long CO2 stays in the ocean must be determined using ocean circulation models. Second, environmental impacts, especially local pH changes affecting marine life, need careful study. Finally, engineering analysis is needed to assess existing technology and identify areas for development. Collaboration between scientists and the oil industry is advancing this field rapidly. Direct injection of CO2 into the ocean can be environmentally beneficial on a global scale, but local impacts must be managed. The main concern is lowered pH, which can affect non-swimming marine organisms at depths of 1,000 meters or more. However, studies suggest that careful design of injection systems can disperse CO2 effectively, minimizing or even avoiding harmful pH changes. Ongoing research aims to ensure that ocean storage is both effective and safe for marine ecosystems. The oil industry has driven significant advances in undersea technology, making ocean CO2 injection increasingly feasible. From deep-sea pipelines to advanced monitoring systems, these engineering solutions are crucial for safe and effective sequestration. As technology continues to improve, the costs and risks associated with ocean storage are expected to decrease, paving the way for larger-scale projects. Carbon management and sequestration offer a unique opportunity to address climate change while still benefiting from fossil fuels. By capturing and storing CO2, we can reduce greenhouse gas emissions and help stabilize the climate. However, realizing this opportunity requires overcoming technical, economic, and environmental challenges. Continued research and innovation are key to making carbon sequestration a practical part of our climate strategy. One of the biggest challenges is reducing the cost of CO2 separation and capture at power plants. Among the plant types studied, advanced coal plants like IGCC have shown the lowest incremental cost for CO2 capture. This suggests that with further improvements, coal could remain competitive with natural gas even in a carbon-constrained world. Ongoing research focuses on making capture technologies more efficient and affordable. Another major challenge is verifying the feasibility of various storage reservoirs, both geological and oceanic. This involves understanding the long-term fate of stored CO2 and addressing environmental and safety concerns. Comprehensive monitoring and risk assessment are essential to ensure that storage sites remain secure and that any potential impacts are managed responsibly. Carbon sequestration should be seen as part of a broader climate strategy that includes improving energy efficiency and expanding non-carbon energy sources. No single solution will be sufficient on its own. By combining multiple approaches, we can address climate change more effectively and at a reasonable cost, ensuring a sustainable energy future. Policy measures such as carbon taxes and economic incentives play a crucial role in making CO2 capture and sequestration projects viable. The Norwegian carbon tax, for example, made the Sleipner project economically attractive. As more governments consider carbon pricing, the financial case for sequestration will strengthen, encouraging wider adoption and investment. CO2 sequestration is a global challenge that benefits from international collaboration. Projects like Sleipner are monitored by researchers worldwide, sharing data and best practices. Such cooperation accelerates learning, spreads innovation, and helps build the knowledge base needed for safe and effective carbon management on a global scale. Looking ahead, research will focus on optimizing capture technologies, improving storage site characterization, and developing robust monitoring systems. Sensitivity analyses and modeling will help identify the most impactful variables, guiding investment and policy decisions. The goal is to make CO2 sequestration safer, more efficient, and more affordable for widespread adoption. Public understanding and acceptance are vital for the success of CO2 sequestration projects. Transparent communication about risks, benefits, and safety measures can build trust and support. Engaging communities early and addressing concerns proactively will help ensure that projects move forward smoothly and responsibly. Effective monitoring and verification systems are essential for ensuring that stored CO2 remains securely contained. Technologies such as seismic imaging, pressure sensors, and chemical tracers help track CO2 movement and detect any leaks. Ongoing monitoring provides confidence to regulators, operators, and the public that sequestration sites are performing as intended. Long-term stewardship of CO2 storage sites involves ongoing monitoring, maintenance, and risk management. Clear regulatory frameworks and liability provisions are needed to ensure that storage remains safe for decades or even centuries. The experience of the oil and gas industry provides valuable lessons for managing these long-term responsibilities. While CO2 sequestration offers many benefits, it also carries potential risks, such as leakage or unintended environmental impacts. Risk assessment and mitigation strategies are essential to minimize these dangers. By learning from pilot projects and continuously improving technology, we can address these risks and ensure safe, effective carbon storage. Investing in CO2 capture and sequestration can create new economic opportunities, from technology development to job creation in engineering, construction, and monitoring. As the market for carbon management grows, early movers can benefit from leadership in a critical sector for the low-carbon economy. Balancing costs and benefits will be key to realizing these opportunities. In summary, CO2 sequestration is a powerful tool for addressing climate change, offering both opportunities and challenges. With continued research, innovation, and collaboration, we can overcome technical and economic barriers. By integrating sequestration with broader energy strategies, we can move toward a more sustainable and climate-friendly future. This work draws on research supported by the U.S. Department of Energy and contributions from many scientists and engineers worldwide. The field of CO2 sequestration is advancing rapidly thanks to their efforts. For those interested in learning more, a wealth of technical literature and case studies is available, providing deeper insights into the science, technology, and policy of carbon management.